Already this semester, we've seen a number of binary relations that describe relationships between different objects. But to talk more precisely about a relation like less than or equal to, or divides, and to make comparisons between different relations, we need a formal definition. We define a relation R in terms of the sets A and B that are respectively the things that could appear on the left-hand or right-hand side of the relation. And our definition specifies which elements of the two sets are related by the particular relation. So when we say that 5 is less than or equal to 7, we are saying that the pair 5, 7 is an element of the relation less than or equal to. And since the relation is a subset of the Cartesian product of these two sets, the relation itself is a set of ordered pairs. All of these ordered pairs consist of an element of set A and an element of set B that are related by relation R, and so R will be some of the possible ordered pairs of this form. And so then if we want to say that the less than or equal relation holds between two numbers, then we could say that the ordered pair of those numbers is an element of the relation less than or equal to. And for different numbers where the relation doesn't hold, then we would say that that ordered pair is not an element of this set. This may seem like a very strange way to talk about relations like the examples I've listed here, but by defining it in terms of a set of ordered pairs, it will be much easier for us to talk about properties of relations and how different relations compare to one another. Often we will have relations where the sorts of objects that can appear on both sides of the relation come from the same set, like the set of integers, in which case we can talk about a relation on that set, such as divides being a relation on the set of integers. If we have the set 1, 2, 3, 4 and the relation less than, we can list all of the ordered pairs that belong to that relation. So because 1 is less than 2, we say that the pair 1, 2 is an element of the less than relation on set S. And similarly, 2, 3 and 3, 4 or 1, 4, all of these ordered pairs are members of this relation. We can talk about the inverse of a relation as the relation we would get if we reversed the order of every ordered pair in the original relation. And so if we took the inverse of the less than relation on set 1, 2, 3, 4, we would get a relation with 6 elements that are all of these pairs reversed. And in this case, the inverse of the less than relation is the greater than relation. The reason for this formal specification of a relation is that it will let us talk about properties of different relations. So let's define some properties now. We can classify different relations based on whether they have or don't have certain properties that we can define. We call a relation reflexive if, for every element of the set, that element is related to itself. An example of a relation that's reflexive is the equality relation. Every element is equal to itself, and so the pair of an element and itself is always an element of the equality relation. An irreflexive relation is one where an element is never related to itself. So an example of an irreflexive relation is the not equal to relation. But of note, these definitions are not negations of one another. If we were to negate one of these for all statements, we would instead get a there exists statement. And so it is possible to have a relation that is neither reflexive nor irreflexive. And that would happen if there is some element of the set that is related to itself and another element of the set that is not related to itself. We call a relation symmetric if, whenever A relates to B, B also relates to A. It might seem like antisymmetric should be the opposite of symmetric, but that's not what it means. We call a relation antisymmetric if the only time that A relates to B and B relates to A is when A and B are the same object. Here I've used slightly different notation, saying that A relates to B, but that means the same thing as AB being an element of the relation. So here we're saying that A relates to B and B relates to A would mean that A and B are the same object. And finally, transitivity is what we might expect, that if A relates to B and B relates to C, that means A relates to C. To get a sense for these definitions, let's think about some example relations on the set of integers and whether those relations have these various properties or not. Take a moment to pause the video and think about, for each of the relations less than or equal to, less than, equal to, not equal to, divides, doesn't divide, and is congruent to mod 2, do those relations satisfy each of these 5 properties or not? Congruence mod 2 was defined on the first review, but we can also think of it as equivalent to the has the same parity as relation that we saw in an in-class activity. Congruence mod 2 means that the difference is divisible by 2, and that only happens for two numbers that are either both even or both odd. Now that you've paused to think about this, I'll talk through some of the answers, but leave the rest for you to double check on your own. The less than or equal to relation on the integers is reflexive because every integer is less than or equal to itself. It's antisymmetric because if A is less than or equal to B and B is less than or equal to A, then we can conclude that A and B are equal. It's transitive because if A is less than or equal to B and B is less than or equal to C, then A is less than or equal to C. And it's not irreflexive because we have examples like 0 is less than or equal to 0 of a number being related to itself. And it's not symmetric because we have counterexamples like 1 is less than or equal to 2, but 2 is not less than or equal to 1. The not equal to relation is irreflexive because for every integer, that integer and itself is not a member of the not equal to relation. And it's symmetric because if we have A not equal to B, then we can conclude that B is not equal to A. It's not reflexive because of many counterexamples. In fact, it's never the case that an integer is not equal to itself. It's not antisymmetric because of counterexamples like 1 is not equal to 2 and 2 is not equal to 1, but we can't conclude that 1 equals 2. And it's not transitive because we can have 1 is not equal to 3 and 2 is not equal to 3, but 3 is not equal to 3. The divides relation is reflexive and transitive, but doesn't have the other properties. And for this case, I want to be a bit more formal about proving which of these properties hold and don't. To prove that the divides relation on the set of integers is reflexive, we want to show that for any integer, that integer divides itself. To show that x divides itself, we need to give an integer that we can multiply by x to get x. That integer is 1, so we can conclude that x divides x. And since for every integer, that integer is related to itself, we conclude that the relation is reflexive. To prove that divides is transitive, we need to show that if A divides B and B divides C, then A divides C. So our hypothesis is that we have 3 integers where A divides B and B divides C. And we eventually want to conclude that A divides C. When we unravel definitions, we know that A divides B means there's some integer x such that AX equals B, and similarly there's an integer y such that BY equals C. So then we can substitute for B and get that AXY equals C. And since x and y were both integers, their product is an integer, which means that A divides C, which means that the divides relation on the set of integers is transitive. To prove that the relation does not have the last 3 properties, we need to give counterexamples. For irreflexive, we just need an integer that relates to itself by the divides relation. So 1 divides 1 provides a counterexample. To show that it's not symmetric, we need an example where A divides B, but B doesn't divide A. We can use the fact that 1 divides 2, but 2 doesn't divide 1. And antisymmetric would mean that if A divides B and B divides A, then A and B would be equal. And we've already seen a counterexample in one of our in-class activities. An integer and minus that integer divide each other, but are not equal, so we can pick our favorite integer as a counterexample. The way we showed that divides is not symmetric is by giving an ordered pair that is in the relation, but the reverse of that ordered pair is not in the relation. And thinking about reversing the ordered pairs brings to mind the inverse of a relation. And so we can think about the connection between relations being symmetric and the inverse of a relation. In fact, a relation is symmetric if and only if it's equal to its inverse, which is the same as saying that reversing every ordered pair in the relation would give us back exactly the same relation. For an if and only if proof, we have two directions to show. So first, we want to hypothesize that we have a symmetric relation and show that this means that the relation must be equal to its inverse. And for the other direction, we want to hypothesize that we have a relation which is equal to its inverse and show that this means the relation must be symmetric. So we hypothesize that we have a relation that's equal to its inverse and want to conclude that the relation is symmetric. Since our goal is to show that R and R inverse are equal, and we defined a relation to be a set of ordered pairs, we now want to prove that these two sets, R and R inverse, are equal, and we prove that two sets are equal by showing that they are each a subset of the other. So let's begin by hypothesizing that we have an element of R. Of note, it's possible to have a binary relation that's always false, so there would be no elements of that relation. But if that's the case and R is the empty set, then we trivially have that R is a subset of R inverse. So if we have an element of the relation, then, because R is symmetric, we know that if AB is in R, BA must also be in R. And now, by the definition of R inverse, we know that the reverse of any element of R must be an element of R inverse, and in particular, the reverse of BA must be in the inverse relation. And so now we've shown that every element of R is also an element of R inverse. So we have that R is a subset of R inverse. And now we would need to show the reverse direction, that R inverse is a subset of R. We could start with an element of R inverse, and we know that its reverse must be in R. Since R is symmetric, the reverse of that must be in R, and so that means that the element we started with from the inverse is an element of R. For the reverse implication, we want to show that R is symmetric, and the symmetry property is that whenever AB is in R, we also have that BA is in R. So we're showing an if-then hypothesis. So let's suppose that we have some element of the relation, and we want to show that the reverse of this ordered pair also belongs to the relation. Again, we have the possibility that there are no elements of the relation, but in that case, the if-then statement would be vacuously true. And here, we know that BA is an element of the inverse relation. But since the relation is equal to its inverse, that means that BA is also in R. And since the reverse of any element of the relation is in the relation, we conclude that it's symmetric. So we've seen that for different relations, different combinations of reflexivity, anti-reflexivity, symmetry, antisymmetry, and transitivity can hold or not hold. But there's one specific combination of these properties that is of sufficient interest to be worth defining separately, and that's the idea of an equivalence relation. If a relation is reflexive, symmetric, and transitive, we call it an equivalence relation. An example of an equivalence relation is congruence mod n. Of note, congruence mod n is only a well-defined relation if we specify a particular n. For example, congruence mod 4 or congruence mod 17 are valid relations. But congruence mod n turns out to be an equivalence relation for any positive integer n. And so I will do these following proofs in terms of a general n, but it's worth keeping in mind that congruence as a relation only makes sense if we fill in a specific integer for n. To show that a relation is an equivalence, we need to first argue that it is reflexive. To show reflexivity, we want to argue that every integer relates to itself. So we can hypothesize that we have some integer x, and we want to conclude that x is congruent to itself mod n. Now we unravel definitions, and our definition of congruence mod n was that n divides the difference between the two values. So our goal is to show that n divides x minus x, but x minus x is 0, and for any integer n divides 0. So we conclude that congruence mod n is reflexive. For symmetry, we want to show that whenever x relates to y, y relates to x. So we can hypothesize that we have two integers that are congruent mod n. And we want to conclude, based on this, that y is congruent to x mod n. When we unravel the definition in our hypothesis, we get that n divides the difference between x and y. And unraveling further, the definition of divides tells us that there is some integer a that we can multiply n to give us x minus y. And if we think about the definition that we are trying to reach from the other end, we want to show that n divides y minus x. And so we want to show that there's some integer that we can multiply by n to get y minus x, but we can get there by just multiplying both sides by -1 from here. And since minus a is also an integer, we conclude that n divides y minus x, and y is congruent to x mod n, and therefore congruence mod n is symmetric. For transitivity, we want to hypothesize that x is congruent to y and y is congruent to z. And from this hypothesis, we want to conclude that x is congruent to z mod n. When we unravel definitions, we get that n divides x minus y, and it also divides y minus z. And when we unravel these definitions of the divides relation, we have that there are integers a and b that we can multiply by n to get these two differences. And our goal is to eventually show that n divides x minus z. And so we want to eliminate the y. So we can solve for y in one of these equations and then substitute it into the other. I've made some space so that we can now rearrange. And now we can factor out the m. And since a and b were both integers, a plus b is an integer, and we've shown that n divides x minus z, and from that we conclude that congruence mod n is also transitive. Part of the reason why it is useful to specifically define equivalence relations is that an equivalence relation allows us to partition a set into equivalence classes. In talking about an equivalence relation, we can think of all of the things that are equivalent to a particular element A, and we call that an equivalence class. So the equivalence class of element A is a subset of S where we have collected all of the elements that are related to A by the equivalence relation. Of note, since the equivalence relation is reflexive, we know that A is in its own equivalence class, and since it's symmetric, we know that A must be in the equivalence class of B, and since it's transitive, we know that anything that's in B's equivalence class is also in A's equivalence class. And so, when we build this set, we end up with a whole bunch of things that are all related to each other by the equivalence relation in the equivalence class of any given element. If we have an equivalence relation on set S, and we collect up all of the distinct equivalence classes, then we will have partitioned the set S. By partition, we mean that we will have split up all of the elements of the set such that every element goes in exactly one of the equivalence classes. We haven't formally defined partitions of a set, but we can state precisely what we mean here. When we split the set up into equivalence classes, every equivalence class is a subset of S, because we chose only elements that belonged to the set. All of the equivalence classes are also non-empty, because under an equivalence relation, an element always relates to itself. And if we take any two equivalence classes, they are completely disjoint. That means they don't have any elements in common, because if they did have two elements in common, then those elements would be related under the equivalence relation, and all of the things in the second equivalence class should have been in the first equivalence class instead. And if we union together all of the equivalence classes, we get the original set, so there are no elements that don't belong to some equivalence class. This property is proved in full in the book, and I encourage you to read that proof and ask questions about it. But I want to talk through an example of an equivalence relation on the set of integers and the equivalence classes that it induces. Let's think about the congruent mod 4 relation. And since we just proved that congruent mod n is an equivalence relation for any n, we know that this is an equivalence relation on the integers. So, how many distinct equivalence classes do we have for congruent mod 4? Well, we can start by picking an element of the integers. I'll pick 0, and thinking about what's in its equivalence class. Well, this equivalence class contains the set of all things where the difference between that number and 0 is 4. So this contains 0 and 4 and minus 4 and 8 and minus 8 and so on. Now we can pick something that was not in the equivalence class of 0 and think about its equivalence class. The equivalence class of 1 is all of the things that are congruent to 1 mod 4, and that's all of the integers that have a difference from 1 that is a multiple of 4. So this set includes 1, -3, 5, -7, 9, and so on. We still haven't covered all of the integers, so let's pick something else that is not yet in one of these equivalence classes. We'll pick 2. And its equivalence class is the set containing 2, -2, 6, -6, 10, -10, and so on. And finally, we have the equivalence class for 3. And now we have a set of equivalence classes that cover all of the integers. Every integer is in at least one of these 4 sets, and in fact there's no overlap between these sets, so every integer is in exactly one of these sets. And so we can think of the equivalence classes of the congruent mod 4 relation as corresponding to the remainder that you get when you divide an integer by 4. And so the names of these equivalence classes show us the connection between congruent mod n and the modulus operator % in most programming languages. In our in-class activity, we'll think about relations between and on sets, and we'll think about, for some of those relations, which of the properties do they satisfy, and if they satisfy reflexivity, transitivity, and symmetry, then we will think about the equivalence classes of those equivalence relations.